Hi guys, and now we are into the good stuff, which is actually becomes very practical, and you can actually look at a lot of data points to understand a lot of distributions henceforth, right? So we are looking at normal distribution, right? Remember, when we actually looked at visualization data, we all saw that bell curve that we were talking about. That's nothing but a normal distribution, right? Stock market returns follow a normal distribution, not a perfect normal distribution. There's nothing called as a perfect normal distribution, but yes, it replicates very similar to a normal distribution, right? And hugely used in investments, when you want to actually hypothesize or even take decisions related to risk, because unless and until you know what is the range of things which can actually go on, you can't really make any predictions or you can't really take any decisions, right? So you need to understand that a normal distribution, now this might be a little bit of theory, but yes, it makes sense that it can be explained by two parameters, which is its mean and standard deviation or variance, right? Which is normal, which we always know that we can actually explain a distribution, a normal distribution, using two parameters, which is its mean and its volatility from the mean, right? So a normal distribution has a skewness of 0. Remember skewness, which means a skewed distribution could look something like this, right, on the right hand side, or it could look something like this to the left. So this is skewed to the left, skewed to the right, and this is skewed to the left, right? And kurtosis, which means the height, is equivalent to 3, right? Now there is a lot of calculation for this, but it's actually not required for the exam. But you should know that a standard normal distribution, right, will have a kurtosis of 3 and a skewness of 0. Okay, so that means very symmetric, right? Now let's look at the relationship between the probability density function and a cumulative density function. We have already covered this, but in terms of visual, how does it look? So whenever we look at uh, you know relative frequency, and we also looked at cumulative relative frequency, right? uh, which is to say that when we're talking about relative frequency, we are saying that okay, how many number of observations are between -5 to let's say 2%. And if we said that okay, there are about 20% observation lying between these two, then we are looking at relative frequency, right? If we were to create a second range, which is to say that okay, from -2 onwards to let's say so +2 onwards to let's say 5%, what is the amount of relative frequency? So we say that okay, that's about 30%. So what would be the cumulative relative frequency? That would be up till here it's 20%, then up till here it's 20 plus 30, which is 50%, right? So if you also remember in the previous slides when we discussed this, an absolute frequency, looks something like this, right? I mean, you've got various bars of the frequencies happening, but a cumulative relative frequency does not really actually happen like this, because as we keep on progressing across ranges, the line would be something like this, right? Because all it is trying to say is that until here, until this point, these are the amount of observations which are possible. So out here also it's exactly the same, right? We are talking about a PDF, which is probability density function, showing out here, and an equivalent of this would look something like this, right? And if you see, for various points it has shown accumulative density functions, right? So if you see this almost a half point out here, so in a cumulative density function chart, this would also be half, but the line is obviously a curve, right? Something like this. Sorry, something like this, right? So that's all that it means out here, right? Now let's look at normal distribution going further. You might remember that we actually plotted the Nifty 50 distribution, right? And this is actually daily returns of Nifty 50, and you can see that this is the mean. So the mean is somewhere around here, right? That's 1%, and looks pretty symmetrical, but it's not exactly a standard normal distribution. It is not an absolute normal standard distribution, because it does have some extreme events that tends to happen in stock markets. For example, the 2008 market crisis, right? So they have fatter tails, right? Fatter tails means, the extreme possibility of lower or higher returns, right? But what the reason why we are discussing this is because the stock market distribution does obviously have a higher kurtosis than 3, because a standard normal distribution would look something like this, right? But obviously the nifty 50 distribution is taller than this. That means the kurtosis is greater than the standard normal distribution, right? That was what the objective is, right? And if you remember, we also calculated, you can easily calculate kurtosis in a spreadsheet. The kurtosis of nifty 50 distribution is 9, and a standard normal distribution has a kurtosis of 3, which means obviously it has slightly more height. And also in terms of skewness, a standard normal distribution has a skewness of 0, but the stock market distribution, when you actually calculate the skewness, it does still have some negative skewness. Okay, let's look at the probabilities using the normal distribution. Okay, so this is what I was talking about. These values you should remember but not memorize. Get the idea that uh, in a normal distribution, about 68% of the observation should lie between this region, right? So if you see 34 out here, 34 this side, 95% within 2 standard deviations. So if you were to take the entire this area, so that would comprise almost 2 standard deviation. And if you consider 3 standard deviation, then you're looking at almost 99% of the observation, right? So that's some stats to remember, uh, because those are just facts. Okay, let's look at an example. So chief investment officer of fund XYZ would like to present some investment return scenarios to the investment committee, right? With some indicative numbers, assuming daily asset returns are normally distribution. So the assumption is that the data is normally distribution, right? So there's an investment officer and he's trying to present some numbers to the committee, and there are some questions which have been asked. Okay, so the first question, and assuming that this data is entirely normally distribution, the first question is, what is the probability that the returns would be less than 1 standard deviation? Less than 1 standard deviation. Okay, so then we're basically talking about this area. Okay, now the way to do it is actually to look at a z table. So z table, what it does is, for different z values, or whatever standard deviation that we are looking at, right, it gives us what is the probability till that level. Okay, so cumulative. Okay, so if you're looking at -1 standard deviation, right, equal to 1 standard deviation below the mean, that means we are looking at -1, right? So if you were to go to a z table, you would actually find out, uh, considering that is exactly -1. If it was 1.01, then we would look at this section. But since it's exactly -1, then we are looking at here and here. So which means 15.86% probability that the returns will be below 1 standard deviation of the mean. First question. Okay. Second question is between plus and -1. But I guess we already know that, right? Because we already know that within 1 standard deviation, 68% of the observations lie, right? So the second question will automatically get you 68. But if you were to actually see, you can actually do that as well. So if you see that till 1 standard deviation, okay, till 1 standard deviation on the positive side out here is about 84.13, right? And if we were to look at till -1, which is on the other side, right? Now the way to do that is just to take 1 minus 0.8413, because this is a cumulative distribution, so it whatever happens on the right is also equivalent to the left, right? So if we have probability of this is, let's say, 84.5%, then it's obvious that the other side, which is let's say the number of possibilities happening below 1 standard deviation, is going to be 1 minus 84.5, which is 15%, right? And if you actually just reduce 84.3 minus the 15.86, you will get 68.3%, right? Which is the answer to question number 2. Let's look at question number 3. What is the probability that returns would be less than or equal to minus 2 standard deviation? I directly go to the z table. Minus 2, that's our standard deviation. And if you look at the probabilities, that is 0.002 2.75, that is nothing but 2.275%, right? Question number 4 asks, how far must returns fall in terms of standard deviations? They're asking you standard deviation instance of probability, right? Below the mean for the probability equal 95%. Now we already know that, right? We know that it's 2 standard deviation, but we can still try to almost 2 standard deviation, but we can try to get the exact answer by looking at the z table, right? If you look at this point out here, that's 94.29, or rather going out here, this is more exact, so that's 1.65 standard deviation for it to have 95% of the observation, right? So that's the answer for question number 4. Now we're discussing standardizing the random variable, because not always are you going to have a standard normal distribution, because if you're trying to find out anything related to a stock market plot that you're trying to do, it's not standard, right? It replicates standard, it's almost equivalent to standard, but it's not actually standard. So how do you standardize? Because the z table out here is related to standard, so you can't really use the same values which you're calculating on a different distribution out here, because it's not going to work, right? Because your values are never going to match. So how do you match? So that's what this formula is about, and it actually makes sense, right? What you're trying to do is, whatever value that you're dealing with, where x is the random variable, right, mu is the mean, and sigma is the standard deviation. So if you're looking at a value of 10, let's say you had a value of 10, right, and you wanted to find out the probability or the location of that data, right? So what would you do? So all you would do is that you would take 10, right, and your mean is 5, so you have reduced whatever value you are dealing with minus the mean of your data set. So that gives you the difference between the mean, the distance between the mean and the value that you are looking at, which is 5. And then you just divide by the standard deviation of your data set, which is, let's say, 1.5. So it gives you 3.3. So now what has happened is, if you realize, by dividing the distance from the mean by the volatility, you've actually standardized the distance itself. So you get a z-score of 3.33, right, in the normal distribution table, right? So that's what we mean by standardizing the random variable, right? Let's look at a question out here. Assuming that the portfolio mean return is 12% and the standard deviation of the return is 22%, what is the probability that the return will exceed 20%? This is the real use of a z table and all these calculations that we're trying to do, right? So we know that the mu is 12%, and we are looking at a random variable of 22%, which is x is 22%. And the standard deviation, okay, so that was standard deviation, sorry. Standard deviation is 22%, mean is 12%. And what is the probability that the portfolio will have returns greater than 20%? It's very simple. Since 20 is the random variable, so we'll do 20% minus 12%, the mean, divided by 22, okay, 0.36. Now let's try to look at, 0.36. Now let's try to find out in the z table where this is. Okay, so we have standardized the value. So 0.3 and the decimal place is out here. So the intersection of these two will give you 6406. Now look at the question first. What is the probability the return will exceed 20%? Okay, so this is below 0.36. So what is the possibility that this will be higher than this? If this is 64.04%, then this is nothing but 1 minus 64.03%, or this answer. So that's how you use standard normal distribution. It's very simple. If you get used to it, it's very easy. What is the probability that return will be between 12 and 20%? Again, so you've got two z values to calculate. So very simple again. All you need to do is 12 minus 12, which is the mean, and divided by the standard deviation of 22. So this is almost equivalent to 0, and this is 0.36. Now let's look at a z table. So if we were to look at 0, then we are dealing with 50% probability. So if I were to draw this, this is how it will look. So until 0, we've got 50%. And for 0.36, which is this, so until here, we've got about 64%, right? And until here, we've got about 50%. So if you just reduce it, you will get the answer. That is about 14%. And that should be the answer, correct? Okay, so I will leave you to do question number 3 by yourself. The question is, you can buy a 1-year T-bill that yields 5.5%. The yield is effectively a 1-year risk-free interest rate. What is the probability that your portfolio will be equivalent to or less than 5.5? So the question is actually asking you, what will be the returns? What is the probability of returns falling below 5.5? Pretty simple. X is 5.5. Go ahead and do the calculation.